Hey everybody, welcome to another virtual Mrs. Duncan chemistry lesson. Today we're going to finish up Unit 7, the mole unit, and then you're going to work on another lab where you're going to do a virtual version of the copper-silver nitrate reaction and practice the big skill of basic stoichiometry, which we're going to learn about today. So if you're going to take notes with me, we're going to go right to page 7. So we're going to skip page 6. If I have time at the end of the year, I will definitely go back and teach you that calculation. But for now, efficiency is our #1 game. So we're just going to go right to page 7, and we're going to do 7 and 8 today. And then we'll transition over to the lab, and you'll work on that virtual lab. So page 7 in the notes. Just as a reminder, I don't have my stylus, so I'll be using my finger. So bear with me. I'll be as neat as I can. But remember, the completed notes are posted on Google Classroom. So if you need any kind of clarity as to what I'm writing, just consult that or ask Mr. Nagel. He knows his stuff. All right, hold on, let me share my screen and then we'll jump into it. Page 7 in the notes, please. All right. Okie doke. All right, today we're going to learn just like, basic stoichiometry. The good news is on like a fundamental level, you probably kind of already know how to do this, but not in the context of a chemical equation. So let me show you what I mean. All right, let's pretend I had this recipe for making chocolate chip cookies. And I don't think the cookies would be very good, but let's pretend this is my recipe. 1 cup of flour plus 4 eggs, that's ridiculous, plus 1/2 cup of sugar, plus 1 cup of butter, plus just 1/2 cup of chocolate chips would make 12 chocolate chip cookies. Okay, so that's like my recipe for making 12 chocolate chip cookies. Well, what if I wanted to, wish I had a stylus. What if I wanted to make not 12 chocolate chip cookies? What if I wanted to double the recipe and make 24 chocolate chip cookies? So my question to you is, if I want to double the recipe and make 12 chocolate chip cookies, or 24 chocolate chip cookies instead of 12, how many cups of butter would I need? Okay, 2, right? If I wanted to make twice as many cookies, twice as much product, I would need twice as much of every reactant, or twice as much as every ingredient, or in this case, 2 cups of butter. Congratulations, you just did stoichiometry, but in the form of a recipe, not a chemical equation. Well, what if I wanted to make half as many cookies? What if I wanted to make 6? And that's a 6, sorry. What if I wanted to make 6 cookies instead of 12? Okay, I'm on a diet or something. Well, if I wanted to make 6 cookies instead of 12, how many eggs would I need? Well, I would need half as many eggs, so 2 eggs. Congratulations, you just did stoichiometry again, but again, in the context of a recipe for chocolate chip cookies instead of an actual chemical equation. So, what's stoichiometry? Well, it's essentially what we just did. They're calculations based on a balanced chemical equation, based on the quantitative or numeric relationships in a balanced chemical equation. So it's kind of like adjusting a recipe. Like this one, if I wanted to make 2 grilled cheese sandwiches, instead of just 1, I would need to double the amount of each ingredient. I would need 4 slices of bread and 2 pieces of cheese. But instead of thinking about it in terms of food, we're going to think about it in terms of reactant and product molecules, specifically moles of reactant and product molecules. So write down mole ratios and coefficients, and then let's talk about it. So I'll just pause a second mole ratios, coefficients, and then we'll go from there. All right, so here is a balanced chemical equation for actually, we did this in the lab. Remember when we burned the magnesium and it was like really bright and kind of cool, or pretty cool. Let's say I wanted to do this synthesis reaction in red up here at the top. I want to combine magnesium and oxygen to make magnesium oxide. So coefficients, kind of similar to subscripts, you can think of them two ways. You can think of it as like I would need 2 magnesium atoms for every 1 oxygen molecule to produce 2 molecules of magnesium oxide. I mean, you can think of it that way in terms of individual atoms and molecules, but honestly, it's not very practical. Making just 2 molecules of a substance is pretty difficult. I might venture to say impossible to do such a small scale reaction. So instead, when chemists do chemical reactions, we do them with moles of molecules, or quantities equivalent to 6 or on the order of 6.02 times 10 to the 23rd atoms and molecules of our reactants and products. So what I'm saying here in the notes, when I say your coefficients, they give us the mole ratios of reactant and product molecules. What we really think of them as in the real world is, in this case, for every 2 moles of magnesium that I react with 1 mole of oxygen, O2, I'll produce 2 moles of magnesium oxide molecules. So it's a ratio similar to like cups or teaspoons in a recipe, but we're thinking about not cups and teaspoons, but entire moles of molecules. All right, so let me just throw a question at you and you see if you can answer it in your head. What if I wanted to make 4 moles of magnesium oxide molecules? How many moles of magnesium would I need to make 4 moles of magnesium oxide instead of just 2? Well, if I wanted to make twice as much of this, I would need twice as much of each reactant, right? So I would need 4 moles of magnesium for every 2 moles of oxygen to make 4 moles of magnesium oxide, right? If I want to make twice as much product, I need to use twice as many of each reactant molecule. Same thing, if I wanted to make only 1 mole of magnesium oxide, half as much, I would need half as much of each reactant. I would only need 1 mole of magnesium for every half a mole, 0.5 moles of oxygen. All right, that is stoichiometry, at least on the level we talk about it in this class. So I think I talked about a lot of this already. I don't remember if you have to fill this in your notes, but what we're saying is those coefficients, we think of them in terms of moles. This balanced chemical equation tells us that for every 2 moles of magnesium, we react with 1 mole of oxygen. We make 2 moles of magnesium oxide. Okay. All right. So before we do more practice on that level, let's back it up and let's just talk about straight up mole ratios. Mole ratios relate in terms of moles, either reactant molecules of one substance to reactant molecules of another, reactant molecules to product molecules, but mole ratios just straight up come from the coefficients. Oh man, the coefficients. This is a lot of work to fix this. You know what I'm trying to say here, right? Coefficients. The mole ratios come from the coefficients. I hate not having a stylus. Coefficients from the balanced chemical equation. So if I look at this balanced chemical equation here, it's 1 mole of N2 to every 3 moles of H2 to produce 2 moles of NH3. This is called the Haber process for making ammonia. So if I want the mole ratio of N2 to NH3, well, I just focus on the coefficients. for every 1 mole of N2, I produce 2 moles of NH3. So the mole ratio of N2 to NH3, according to this balanced chemical equation, is 1 to 2. I got that ratio just from the coefficients. Well, what's the mole ratio of H2 to NH3? Same approach. For every 3 moles of H2, I produce 2 moles of NH3 molecules. So 3 to 2 is the mole ratio of hydrogen to, that's ammonia, NH3, according to this balanced chemical reaction. All right, congrats. You can now do a mole ratio. Just look at the coefficients, put them in a ratio to each other. The only catch is, what if, it's not possible in this equation, but what if I do this and I get a mole ratio of 2 to 4? I'm going to give you half credit, and the Regents is going to mark you wrong. You guessed it. Make sure you always simplify your mole ratio down as low as possible. So 2 to 4 would simplify to 1 to 2. So that's the only catch. Simplify your mole ratios if possible. All right. So all right. So let's just talk about one that maybe isn't like so intuitive, that isn't maybe so logical, easy to see. Let's work through this sample problem. How many moles of magnesium are needed to produce 3 moles of magnesium oxide in this reaction? All right, I'm just going to take you through this problem, and then we'll just go through the steps in the notes like we usually do. All right, so step 1 is this. If the equation I give you isn't balanced already, balance it. When properly balanced, this is what you get. 2 moles of magnesium plus 1 mole of O2 would produce 2 moles of magnesium oxide. So you balance it. If you need to, you don't always. So then after it's balanced, or you recognize that it's balanced, you go back to the actual problem. How many moles of magnesium? All right, I'm looking for moles of magnesium. So magnesium is going to be like my X here, what I want, are needed to produce 3 moles of magnesium oxide. So if I wanted to make 3 moles of this substance, how many moles of magnesium would I need to do that? Maybe some of you can tell me it's 3, because these are in a 1-to-1 ratio with each other. For every 2 moles of magnesium I use, I make 2 moles of magnesium oxide. That 2-to-2 ratio simplifies down to 1-to-1. If not, here's what you can do. I was given 3 moles of magnesium oxide in the reaction. That's how much of this substance I want to make. So I go to my given in the balanced chemical equation, and under its coefficient, I would put the moles of that substance I'm trying to make. So since I was told I want to make 3 moles of magnesium oxide, I find magnesium oxide in the equation, and under its coefficient, I put the 3. And then I think about, well, what are they asking me for? They want to know how many moles of magnesium. So I would find magnesium in the balanced chemical equation, and under its coefficient, I put an X, because that's what I'm looking to find. Now from here, I can set up myself a proportion using what I have in the balanced chemical equation. 2 over X moles from the magnesium would equal 2 over 3 moles from the magnesium oxide. I could then cross multiply 2x equals 6, divide the 6 by 2, and I would find that, yes, indeed, I do need 3 moles of magnesium to produce 3 moles of magnesium oxide in this reaction. So if you can't see it, like it's not something logical, this one might have still been logical for some of us. You can use the coefficients in the balanced chemical equation and the information you're given in a problem to set up a proportion, cross multiply, and solve for the unknown, whatever you're being asked to calculate. All right, so basically this is what you see me go through here in the notes. Same practice problem I just went through myself. If I wanted to know how many moles of magnesium were needed to produce 3 moles of magnesium oxide, step 1 is balance the equation. If it's not already balanced, sometimes I'm going to give you ones that are. So that might not always be necessary, but 2 to 2, 2 mg plus 102 makes 2 MgO would work. Sometimes people want to write it down, like what you know and what you want to know. A lot of times I just like circle it in the problem, how many moles of magnesium. I'm being asked to find moles of magnesium. That's my X. My known is I want to make 3 moles of magnesium oxide. So you might just like note it in the problem you're given or write it down if that's what floats your boat. And then if you can't see it based on the information you're given in the balanced chemical equation, set up a proportion using the coefficients from the balanced chemical equation and what you know and what you want to know from the actual problem itself. So just one more time, I want to know, or I'm knowing that I want to make 3 moles of magnesium oxide instead of the 2 the reaction is written for. So I would put the 3 under the magnesium oxide. I want to know how many moles of magnesium it would take to produce 3 moles of magnesium oxide. So under the coefficient for the magnesium, I put an X. That's what I want to know. I bring it down, 2 over X from the magnesium equals 2 over 3 from in front of the magnesium oxide. And then I cross multiply and solve. And I get 3 moles. Okay, that's the idea. Let's run, how many more? 2 more. And then you're going to try the lab 22, I think it is. All right, let's go with this. Given the reaction below, how many moles of sodium? So that's my X. I want moles of sodium are completely consumed in the production of 1 mole of sodium oxide, Na2O. Okay, step 1, this is obviously not balanced, so we're going to balance this thing. To balance this, I need to put a 2 here, a 4 here, and a 1 here. Trust me on that, that's balanced. All right, once I have it balanced, I'm going to use the information from the problem to perhaps set up an equation or logic. Some of us might realize I want to make 1 mole of Na2O. Well, the reaction's written to make 2 moles of that substance. I want to make half as much. So I would need half as much sodium to do that. So I would need 2 moles of sodium to do that. But if you can't see it or you want to double check yourself, I'm looking for moles of sodium. So under the sodium's coefficient, I put the X. I'm given that I want to make 1 mole of Na2O. So under the Na2O, I put the 1. I would then bring it down. 4 over X from the sodium equals 2 over 1 from the sodium oxide. I would cross multiply. 2X equals 4. Divide by 2. 2 moles. I would need 2 moles of sodium to produce 1 mole of sodium oxide, Na2O. Okay, logically or using a proportion, that's how you solve that. All right, last one. This one I think is a little bit harder to see with logic, but yeah, it's definitely harder, but I bet some of you can still do it. This one says, all right, given the reaction below, how many moles of aluminum oxide? So I want moles of Al2O3, that's my X, will be formed when 9.23 moles of aluminum reacts completely with O2. All right, so pro tip, when you're reading these problems, focus on 2 things and 2 things only. What do I know? What do I want to know? The rest of it can be ignored in your mathematical setup, at least at our level of chemistry. So that reacts completely with O2 bit, we're going to ignore it. All we want to know is how many moles of this can we make, or can we make if we use 9.23 moles of aluminum? Step 1, balance it. To balance it, it would look like this, 4, 3, 2. I want to know how many moles of Al2O3. So I want a little moles of this. So under the Al23's coefficient, I'd put an X. Can be formed when I use 9.23 moles of aluminum. So under the aluminum's coefficient, I'm going to put down that 9.23. So then I bring it down, 4 over 9.23 from the aluminum equals 2 over X from the aluminum oxide. When I cross multiply, I get 4X equals 18.46. And basically I need to divide by 4, which I should just do in my head, but all right. So it's going to be all rounded to the hundredths. So we'll go with 4.62 moles, which makes sense because the ratio is 2 to 1. So I would need half, I would make half as many moles of the aluminum that I'm using. But that's the numeric proof that I would produce 4.26 moles of the aluminum oxide if I used 9.23 moles of aluminum. Okay, there you have it. There's your basic stoichiometry. That's basically as far as we go at this level of chemistry. We will practice this more, but for now, you are please going to go head over to Google Classroom and work on lab, I think it's 22. It's the copper silver nitrate reaction. Remember what I've been saying, Mr. Nagel, he is here to help you. So please, if you have questions, ask him. He can assist you, and do the best you can. Good luck. I know you can do it. All right. Goodbye. I'll see you as soon as I can.